Hello, class. Let's go over the setup for Lab 4, what you're going to be doing today in Lab 4. So I'm going to share the screen, and then let's take a look at the lab. Here it is. So Lab 4. So you're going to look at the Brownian motion of small colloidal particles, these little plastic spheres. And we're going to start with a movie. You're going to analyze 3 movies, and you're going to compute the mean squared displacement. And we're going to start with this movie of 1.7 micron meter spheres in water. And so the first step is like what you did in Lab 3, where you import a video of the colloids taken on the microscope in the lab into Fiji. So let's first open Fiji. We launch Fiji, and then we open a movie that I've already, this movie is 200 megabytes. I downloaded it from the web, put it onto my computer. Now I'm going to open it, and it's in this, directory videos. It's the one that's water, 40 times magnification, 1.7 microns. So I open that guy. Now it's 1995 frames long. Just to get things going quickly, I'm only going to add 100 frames. You might want to add 200, 300. I'm not sure I would go much more than 300 because it's going to take forever. We don't want to use the virtual stack, and we want to convert to grayscale. So just for the purposes of illustration, I'm only going to read in 100 frames and process a small area. For the lab, maybe you do 200 frames, you maybe take a bigger area so you get better statistics. But we'll get pretty good statistics with just even the small area and 100 frames. Okay, so I go okay. Now, if I bring my mouse up here, you see the progress of it reading in, and then here it is. I've got a scrub bar down here. Yeah, they're little colloidal spheres. They're wiggling around due to the Brownian motion, the random thermal excitation due to the water molecules. Okay, and we're gonna track these particles. Now, as I said, I don't want to process this whole thing. 1300 by 1000. It's going to take forever if I process the whole thing. So I'm just going to take a rectangular region. Bam! I'm just going to, you see the width and the height are varying in the Fiji scroll bar. Here's something around 300 by 300. Boom. So I'm going to extract that from the whole movie. So that's a image crop. Okay, so now I have my little guy here, and just fewer particles, because that's better. So if we go back to Lab 3, we're going to track the particles, track each individual particle. So we have to repeat what we did last week. That's go to the plugin, come open Mosaic, come down to particle tracker. It asks us, are these 3D data? No, they're not 3D data. So we hit OK. And now we get this particle tracker menu here. It says 5, but for these smaller spheres, the 1.7, I'm only going to use 3, which is the default. I'm going to put my cutoff to 0. I'm going to increase the threshold to 1.2. If I go preview detected, now I see these little red things. They're kind of small, hard to see. So I click a couple times with my magnifying glass. And now you can see that the red outline that indicates the detecting the particle nicely brackets the particle. It's not too big, not too small. Goldilocks, just right. If I want to make it small again, I hit the minus sign on my keyboard and it shrinks back. Okay, and I have my scrubber here that lets me move the movie back and forth. Okay, link range 2. I know from experience, I played around with this movie before I'm recording, and a displacement of 2 worked pretty well for me, which are the values given here. So if we just pull that off to the side. So 2, the only thing I changed was radius is 3 from what was in the lab book, from lab 3. So now I hit OK, and you see it's processing, you know, really quite rapidly. Boom, 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 boom. It's done. It found 1,012 trajectories. And so I can go visualize all trajectories, and I get this kind of colorful thing. Again, it's too small to see. 2 clicks of the magnifying glass, make it larger. Why not do 3? And now if I scrub, you know, I see trajectories. And the reason I get, you know, it says there's 233 particles. If you count, there's like 233 particles, but we get 1,000 trajectories, 4 times as many trajectories. That's because each particle, as it's moving, sometimes moves down away from the image plane, moves out of focus. You see, like this one here is a little bit gray and dim, but then if it diffuses back closer to the focal plane, then it becomes bright and gets detected. So each particle moves in and out of focus. They're not just diffusing in a plane, they're diffusing in 3 dimensions. And as they move away from the image plane, then they get out of focus, they get dimmer, and then the tracker loses them. So we get a bunch of more trajectories than there are particles. And I'm going to do a filter where I'm going to look just for long ones. And so I'm going to type in 90. We set to be 100. I'm going to look for only ones that are 90 or greater. And so then it runs through. It does a quick, okay, found 59 after that. So then these are the 59 trajectories that last 90 frames. And they look all pretty good. The linking is pretty good. I'm happy. So then we come back to lab. So we've done this kind of lab 3 part now. We're ready to move on. So step 1, repeat the steps for tracking colloidal particles outlined above in lab 3 until you have long trajectories that you're happy with. Mine are only 90 long. Maybe you're going to do 200 or 300. I wouldn't do 1,900. You'll go crazy. It takes so long to process. But, you know, maybe you want to do longer, but just, you know, I'm showing you a shorter. Okay, so then select a good trajectory by clicking on the track. Click the MSS, MSD buttons. Okay, so I'll come back to Fiji. Say pick a good one. So I scroll. You know, I don't know. That's a good one, I'm going to say. So I get my, I guess, hand tool. I click. Okay, I selected one. Then it says, right, it says select a good trajectory by clicking on the track. Click the MS/MSD plots button. Click, and it goes frame interval is equal to 0. To perform analysis, it must have correct value. Okay, and it just says ignore it. Click OK. Click OK. Now it comes up with a new menu that we haven't seen. This menu over here. And so in pixel width. So we need to know how many microns per pixel, okay? And so the way we do that is we, I'm not sure. Well, the way we do that is we need a calibration slide. So here on page 7 is a calibration slide. I click on that. It opens an image of a calibration slide. Let me download that image. And here it is, download it. And then I'm gonna bring it into ImageJ. So here's the image. And then I'm gonna bring it into, there's my ImageJ. And that's up here. I'm gonna bring it in. Okay, I have this thing open, I'm gonna have to cancel. Okay, so I canceled, and then I bring it into ImageJ. Okay, so now I'm into ImageJ. I want, there's thick lines, and there's fine lines. Okay, so the distance between each fine line is 10 microns. So to measure that, how many pixels that is. I take this straight line, I draw, I think if I hit shift, yeah, shift, it stays vertical. Now I have a line that crosses the two thick lines. I go to Analyze and Process, Analyze, Plot Profile. Analyze Plot Profile, click. So I see this line. Ugh, what did I do? Window. I must have, I don't know what I did there. With my mouse, I did something bad. Okay, I'm going to try it again. I shift and drag. I've crossed the two thick lines. I go to Analyze, Plot Profile. Here it is. I move it down. Okay, so now this is a thick bar that's dark. So it goes lower, darker, and it's thicker than these other bars. And here's another thick bar. So this thick bar is here. This thick bar is here. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 thin ones. 1, 2, 3, 4, 5, 6, 7, 8, 9 thin ones. So if I stick my cursor here and I drag it out to over here, then what's the distance of that line? So this point here is 408. This point here is 69. So if it was 68 to 408, that would be 340. You know, so this is 339. Oh, 341. 409. 69. Oh, it's exactly 340. So it's 340, and it's 10 microns, 20 microns, 30, 40, 50, 60, 70, 80. So I take 80 microns, I divide by 340, and, you know, 80 over 340 is 0.23. Okay, so I come back to my Fiji. I'm finished with my calibration. I can get rid of that, and my calibration slide and my calibration thing, done. And so now we go back to the instructions of the lab. Here it is. And yeah, it said click the MSD, click the MSD button, and then, you know, a window will pop up prompting you to input the image preferences. So let's get back to Fiji. I've got a single thing here. I click MSD. It says perform analysis must have the correct value. Oh, here is this was the menu that we needed to fill out. The pixel width we just determined was 0.23 microns per pixel. So I'm going to put microns for X and Y and Z, just whatever. Now the time interval between each successive video frame is, there's 30 frames a second, so 0.033 seconds, 33 thousandths of a second per frame, 30 frames per second. So 0.033 seconds, I go, okay. And click OK, enter the time per frame, press OK. Click the MSD plots button again, and a plot will appear. So I click it again, a plot appeared. And then it says, click the MSD button. So we don't want MSS, we want MSD, mean squared displacement. Keep the logarithmic scale checked. What happens when you don't? I don't know. Keep it checked. All right. So then the plot now displays the mean squared displacement, log of the mean squared displacement versus time, and it's log of the time. In addition, 3 numbers will be displayed in upper left. Slope. The slope is the exponent of t from equation 1. So where's equation 1? that should be r squared equals 4 dt. R squared equals 4 dt. So the exponent, this is t to the 1, is 1. So that's what it's supposed to be in this window. So 1.1, 1.09, so, you know, it's like 1.1, it's close. And then this value, 5.7 times 10 to the minus 13 meters squared per second. So the actual calculated value is about half of this. So it's about a factor of 2 off from what we expect for a single trace. And so let's just kind of move this over here. And now we can also go, I think, focus on selected trajectory. Let's say I do that. Okay, then I get this little window. And so this little window, let me zoom in on it. You know, this little window gives me the random walk, you know, of this one individual. And you can see it kind of starts on the left, and then it runs, you know, a little bit, ends up on the right, and it jiggles, you know, it gets kind of far, and then halfways, and then it starts going back to where it started, and then it goes far again. You know, it's a random walk. So let me take another particle. I'm gonna take, I don't know, this guy. Whoops, I gotta go hands. The mouse around there, I got it. And then I go MSD plots. Now the plot appears immediately. I've entered all those parameters. I only have to do it once. I have to still hit the MSD. And now this time the slope is 1.03, very close to 1. The diffusion causes 5.0. So, you know, 5.7, 5.0, it's pretty similar. I don't know, let me take this guy. Okay, so I click that guy. I go plot, MSD, MSD. Now I get 4.3 and 0.95, you know, so, you know, I get many different values. They vary. Every one is a little bit different. I try to click on this guy. And if I go focus on selected trajectory, you know, I can see its trajectory. You know, it starts up there, runs down there. And then I can go MSD, now MSD, and 0.67, so even bigger than the previous ones, 1.2, you know, it's kind of an elongated pattern, so it's a little bit different. So we're gonna have to do we're gonna do a lot of averaging to get a good number, okay? That's the point here. You look at each individual trajectory, it has its own characteristics, but you're going to want to average to get an accurate number. So if I hit the minus, I'm moving my mouse over here, I hit the minus button, it gets smaller. These are my trajectories. So now I'm going to want to take many trajectories. So that's this focus on area thing here. So I'm going to take a square. I indicate the square from the palette in Fiji. You know, I draw a big square. Now I'm going to take all the trajectories in this square. Okay, so I'm going to go click. And, you know, and now it copies that information to this screen here. And so now I'm gonna right click, I go save as, and I'm gonna go results. My clock says 11:51 p.m. So I'm gonna go results 1151 p.m. Okay, and I'm going to save that results from 1.7 water. Okay, so I'm going to just go save, and bam, I've saved it. Okay, and so now we're going to go to MATLAB. Bennett Sessa, one of your grad TAs, wrote a script for you to use. And so we're going to go to MATLAB, and And we're gonna open Bennett's script. So Bennett's code, this one here. Okay, and then read table. It was, what did I say it was? 11 something, I forget. So let me go to the directory. It was in results from 1.7 water, 11:51, right? Results 11:51 p.m. So then I go to MATLAB, I edit this, it's gonna be 11:51 p.m. and then I hit run. Just doing some stuff. Okay, and so let me see if I can liberate this thing from, go like that, make it a little bigger. Okay, so, you know, it's saying 0.355, the literature value is really quite close to that, 0.37. You know, there's many, many trajectories here. I guess 59 different trajectories. The shortest one was 78, and the experiment is this dashed line. The theory is this line. You know, they're, I don't know, different by less than a factor of 2. And then you can, like, you know, zoom in, I guess, see what it looks like, you know, closer in. And so there's a bunch of different trajectories. Some move less far, some move greater distance. But if you take, you know, many, many, many trajectories, and so instead of taking this little 300 by 300 area, I took 1,000 by 1,000, you know, got 10 times more data, you know, you would get a better number. So this is kind of showing you about, you know, how to get mean square displacement, and you would, when you do your final analysis, you take a bigger area. And just why I have your attention, I'm just going to show you a couple things from MATLAB, a few other simulations that just kind of try to build up your intuition. So here's one where I just take one random walk. This one is, you know, 1,000 steps. Okay, and if I take another one, you know, each one looks, you know, a little bit different. They start somewhere. And now I'm going to put 2 of them on the same plot. So these are going to be 2. I'm going to change this variable to be 2. These are going to be 2 random walks. Each starts at the same place at the origin, 0, 0. You know, and then this one ran this way, you know, kind of ran off to the left. You know, the green one kind of ran off to the right. They do just random things. If I do it again, you know, again, one runs one way, one runs the other. You know, this one kind of went this way and this one went that way. They go in random directions. So now if I take many of them, so say I take like 10 and then run it, then you start seeing it looks really more circularly symmetric. They go, so each walk is some kind of elongated, stretched out thing, but the direction it stretches out is completely random. It kind of has to do with which first step it took, and then maybe it keeps going in that direction. But so each walk is kind of an elongated object, but when you do many, many, many times of individual walks, that's why you need to analyze so many colloidal particles. Each colloidal particle over time is like one of these initial trajectories. You want to take many, many independent ones to get the good statistics. And we're going to explore this kind of pattern in Lab 5 more precisely. This is very important for like diffusion and diffusion of chemicals. And one other little illustration I want to show is this one here. So here's 4 different random walks and let me see if I can pull this one out. And so I make this larger. Okay, so then, this, like, look at this one here. So this is the origin where this green is, and this big blue dot is the end of it. Okay, so it starts here, and then you see there's these kind of color-coded dots in between. So every 30 steps, I put a mark, and I change the color of the mark as it progresses along the path. So when you're calculating mean square displacement, you take the distance between this one and this one. These are 30 steps apart, and you square this distance, the net distance, not the total distance it walked, but because it walked here and walked back, that's a delta R, a mean square displacement of 0. But this distance from here to here after 30, and then in the next 30, it goes from here to there. And then in the next 30, it goes from here to there, then here to there, then this dark green, then this lighter green, then this kind of yucky orange, then this orange, then yellow, and then finally the blue. If we look over at like this one, this is, and so this guy started here at the bottom and went up, and right. This one starts at the center, and goes straight left. They all take different directions. Each random walk takes a different direction. So then this guy started here, the first step was here, then kind of, here, there, then it got over to here, then this green, this green, this green, orange, walked over here, yellow, black, back to the end. So and the mean squared displacement then is the difference between each of these successive colors squared. This distance squared plus this distance squared, this distance squared plus the average of this distance squared and this distance squared and this distance squared and this distance squared and this distance squared. That's the mean squared displacement averaged. I take each interval between successive dots, square that. If I have like 9 of them, then I divide by 9 to get my mean squared average for 30 steps. And then I can do this for 20 steps, 10 steps, 5 steps, 1 steps to get the mean squared average as a function of the time. Okay, and so then each step, if I zoom in and I look at each step, some steps are to the left, some are to the right, and I make a histogram, then on average, the steps are 0. You don't go left or right, but there's equal probability of going in either direction, and this is called a Gaussian distribution. And if I plot each displacement of each of these steps, it's just this fluctuating variable. And if I add up all the ones that are 0, I get this value. And if I add up all the ones that are between 0 and 0.1, I get this value. If I add up all the ones that are between 0.5 and 0.6, I get this value. If I add up all the ones that are less than -2, I get this value. So integrating these displacements horizontally gives me this distribution. And then for this one trajectory, for this trajectory here, I get this mean squared displacement as and so for 30 steps, that's what's shown here. To calculate the 30-step mean squared, I take the difference between each of these colored dots, square it, add them together, divide by the number of steps, which is 9, and then that gives me this number here. And then it's given by this formula. The mean squared displacement grows linearly with the number of steps. Time is if I take a step every second, then time is this same as the step number. Okay, so that covers how to work through Lab 4 and a little bit about how to think about and interpret mean squared displacement. So good luck in the lab, and I hope you enjoy it. I'm going to stop now. Good day.